In this video, we're going to look at testing the significance of correlation coefficient, the prediction, and outliers. So in our previous video, we introduced both R, which is the correlation coefficient, sometimes called the Pearson coefficient, and we also introduced the coefficient of determination. So what R does for us is it indicates the strength and the direction of the linear relationship between the two variables, x and y, or whatever variables we are trying to look at for a relationship. You're like, wait a minute, what does the coefficient of determination, or R squared, do for us? Doesn't that give us how strong something is? Well, yes and no. The coefficient of determination tells us what percent the variation in the y is explained by the model. So yeah, it does kind of give us how strong our relationship is, but it doesn't tell us any directionality. Now remember from our last video that when I'm talking about the coefficient of determination, that is just basically R squared. So if we want to assess how significant that relationship is, the significance of the correlation coefficient, we're going to do a hypothesis test. This is going to help us determine if there is a relationship in the sample, and if it is strong enough to represent the entire population. When the correlation coefficient R is computed from the sample, if the data for the entire population were known, then we'd have the correlation coefficient rho that could be used to be directly calculated. Now rho is the population parameter, just like mu is the population parameter for the mean, and P is the population parameter for the proportion. However, since we typically only have the data sample, R is going to serve as an estimate for the unknown population correlation coefficient rho, just like when we use P hat for proportion and we use X bar for the mean. What we're going to do with our hypothesis test, it will enable us to do an evaluation of whether the population coefficient rho is either close to zero or significantly different from zero. This determination relies on both the sample correlation coefficient and the sample size. Here are some assumptions that have to happen for me to be able to have this kind of a hypothesis test. First of all, that we expect it to be linear. In the population, there's a linear relationship that models the average value of y's for different values of x. That we are looking at independent, so the x is not dependent on the y is not dependent on x. And the residuals, those things that are left over, are said to be independent. That it's normal, the y values are distributed normally for any value of x. We have equal variance, that means the standard deviation for all the y values is equal for each of the x values. We are using random, so we have data that is produced from a well-designed random sample or randomized experiment. And we have homogeneity, which is similarity of variance and no influential data points. The standard deviation in this type of calculation is called the error or residual. It is y naught minus y naught hat. You're like, what? Well, give me a moment. It is not an error in the sense of that it is a mistake. The absolute value of the residuals measures the vertical distance between the actual value of y and the estimated value of y. So y naught is the actual value and y naught hat is the estimated value. So in other words, it's measuring the distance between actual and predicted on that from the point on a line. So as an example here is the predicted. We have an x and the predicted y, which is y hat. But the actual data point is this point right here, which is x naught, y naught. If the observed data point lies above the actual line, as in this example here, the residual is positive and the line underestimates the actual value for y. If the observed data point lies below the line, the residual is negative and the line overestimates the actual value of y. So like this point right here. Each data point not on the line will have a residual, and this absolute value of E is the distance from the data point to the line of best fit, this being the line of best fit. The sum of squares, or the sum of squared errors, I should say, the sum of squared errors, also known as SSE, is the summation of all of those residuals, or errors, squared. And the reason is that if you have negatives and positives, if you don't square them, you could end up with 0, and that would lead us down the wrong path. The standard deviation, also known as the standard error, so this is still the same all the way from way back in chapter 2, when we started to talk about standard deviation or the standard error, of the residuals is calculated after you find this SSE. And it is S, again, because we are in the land of samples, is equal to the square root of that SSE divided by n minus 2. The sum of square errors, also referred to as the residual sum of squares, RSS, is the absolute amount of explained variation, where R squared is the absolute amount of variation as a proportion of the total variation. So we talked about R squared. This is that percent of y's that we can be explained by the model, that have deviations from the model. So when you compare the standard deviation of the residuals to the y values given in the data to determine if there are any outliers, the smaller the numbers, the more certain you can be about your regression model. We are going to use in Excel the call, which is equals, and then we're going to do linest, L-I-N-E-S-T. I'm going to grab the column that has my dependent variables first, comma. I'm going to grab my column that has my independent variables second, comma. Then I'm going to write true, true. And this will produce more information than we actually want. So it's going to look something like this. So it's going to give me all of this information. Well, what is this information? Well, this, if we take a look at this box, which is this, gives me the slope. This box, which is this, gives me the y part of the y-intercept. Now, we don't typically worry about the standard error of slope, so we don't need that box. We don't typically, in this class, worry about the standard error of the intercept, so we don't worry about that box. Then we have the coefficient of determination, or R squared. That's this. This tells me that 63% of my y values can be explained with my model. The next thing I'm going to look at is the standard deviation or standard errors. That's this number. This F statistic, I don't worry about that. I don't worry about the regression of sum of squares, so I don't worry about that either. But this gives me my degrees of freedom, which is here. And then lastly, my sum of square errors, which is here. So all the things that are in the blue highlighted are the things that you will need for this class. The other numbers that are given to us, we don't need for this class. When we talk about outliers, we talked about in this last video, is we have outliers that are considered any data points that are far from the cluster or cloud of data points. This could mean that it's off, but close to the line, off somewhere, kind of in space almost, but it's close to the line. And this could also mean that we have numbers that are far away from the line, but above or below my cluster of dots. So we see that an outlier is an influential point if the observed data points are far from the other observed data points and they have a big effect on the slope of the regression line. So to begin to identify these influential points, we can remove it from the data set and see if the slope of regression is changed significantly. I mean, that's a quick way of finding it. So as we take a look, this, like I talked about, is this point way out here, is an outlier. It's not near these clusters. But since it's close to the line, this linear regression line or line of best fit, this point right here is far enough, it's almost on that line, so it is an outlier, but it's not influential. Now, these dots, if I take this data piece and say, oh, that's an outlier, I remove it, I'm going to get almost a straight line here. If I take this data piece and I'm like, oh, wait a minute, it belongs down here, so it's down here, you can see that this data point being down here has moved this line of best fit down. It's changed this line of best fit. This also, moving this data piece, if it was up here, takes my line and moves it up. It changes my line of best fit. So this is an outlier and influential. This is an outlier and influential. This is an outlier, but it's not influential. So to determine if the data has a linear coefficient or linear correlation, we're going to do a hypothesis test of the significance of the correlation coefficient to decide whether or not there's a linear relationship in the data and if it's strong enough to use for the model relationship in the population. There are just two possible ha and ho's. Ha or ho is that rho is equal to 0. The ha is always rho is not equal to 0. So rho equals 0 means that there is no linear correlation between these two sets of pieces of data. And rho equals 0 or not equal to 0 means that there is a relationship, a linear correlation. Now, I just want to caution you, this linear relationship or this linear correlation does not mean causality. X does not cause Y. It just means that there's a relationship between the two. Rho is a population, and it is our parameter. It is our variable that we use for the population. And we are automatically a two-tail test. So when we draw the conclusion, we can do it one of two ways, like we've been doing in all the other videos. We can talk about the p-value, or we can talk about the critical value. So if we test concludes that the correlation coefficient is significant, and it's different from 0, we say the correlation coefficient is significant. We'd say something like, there's a significant evidence to conclude there is a significant linear relationship between these variables, whatever they are, because the correlation coefficient is significantly different from 0. So what does this mean? It means there is a significant relationship between x and y, and it's linear, and we can use this line of regression to model linear relationships between x and y within the population. If the test concludes there is no correlation coefficient, and it's not, well, if the test concludes the correlation coefficient is not significantly different from 0, could be close to 0, but not significantly different than 0, we see the correlation coefficient is not significant. And we'd write something like, there is insufficient evidence to conclude there is a significant linear relationship between x and y because the correlation coefficient is not significantly different from 0. What that means is that we cannot use the linear regression line to do the relationship between x and y in the population. This is going to be really important on your homework or test. And if your hypothesis test says you cannot use the regression line or line of best fit, that means you really truly cannot use that regression line or line of best fit to do a modeling. A couple of things that you're going to need is you're going to calculate the R value, and we use Excel to do this. The formula for the test statistic is going to be T. It's going to be a T distribution. And it's going to be T is equal to, so this is my T calculated, this is my critical value, is equal to R, which is my correlation coefficient, multiplied by the square root of the degrees of freedom divided by 1 minus R squared. The test statistic is a t-value, so we'll use the t.dist.toTail to find the p-value with the degrees of freedom of being n minus 2. The test statistic has the same sign as a correlation coefficient. So if the correlation coefficient is negative, my test statistic will be negative. If my correlation coefficient is positive, my test statistic will be positive. So here's a couple of things to note. R is significant when the absolute value of R, so I don't care if it's positive or negative, is between 0.7 and 0.9. Values between 0.5 and 0.7 are moderately significant. Now notice this is 0.7, which is less than or equal to R. But if I have something that is less than 0.7 and to 0.5, we can say they're moderately significant. And then a scatter plot shows a trend line. The line can be used, but it's only within the domain of the observed X values. If R is not significant, so if my R value is less than or equal to the 0.5 when I take the absolute value of it, which means I don't worry about the negative or the positive, it is the absolute value, or the scatter plot does not show a trend line, then the line should not be used for prediction. If R is significant and the scatter plot shows a linear trend, the line may not be appropriate or reliable for predictions outside the domain of any observed X values in the data. So be careful. Just because you have things that are working out doesn't mean you get to do it outside of whatever the x values start and end with. Sometimes you can, sometimes you can't. If you cannot estimate with a regression line, your estimate is the average of the y values. Now, you're going to ask me, how do I find this if I can't use the line of best fit? And it's right here. Your estimate is the average of the y values. Okay, so if I were asked to show this table, here's this table that shows a poverty rate and cellular use per capita. It is believed there's a strong relationship between poverty rates and cellular usage. That was hard for me. What is the null and the alternative hypothesis? Well, we talked about that before. There really is only one choice for HO, and HO is that rho is equal to 0, and HA is that rho is not equal to 0. Rho does not equal 0, and that's rho, not P. So if I graph the percent of Americans living on or at below poverty line versus cellular, I would put this in as my, quote, x value. This is my x value. And I would grab this as my y value. So this is my y value. And then I would perform a linear regression. So that's pretty easy. We pretty much we can do it with a scatter plot, and then we right-click on a dot, and then it says, hey, what do you want to do with this? And on their scatter plot, you right-click on the dot, and you say, show trend line, and then it'll pop with a screen up on the right-hand side in your Excel, and then you're going to say, put the trend line on there. Now, can you do it without doing all of the graph? And the answer is yes, and we're going to use the line est. If I did the graph, or I use the line est, remember up above, it shows you the things that you need in the right places. My linear regression line is y hat, this is my predicted y values, is equal to negative 2,317 plus 104x. Now you might see this, I wish it was consistent in the homework, I wish it was consistent in the book, I wish it was consistent everywhere. You'll notice that this looks a lot like a slope-intercept form of a line, except for the intercept is first, the slope and the x is second. Just pay attention to what it's asking you to do, because sometimes, well, technically statistics should always be wrote like this, but sometimes it's going to ask you to write it as y hat is equal to the 104x minus the 2,317. Just be aware of that. So I used either lin est, or I can get the information by filling it in a spreadsheet. I'm going to use the lin est. And my R value is 0.50477. So that's my R value. It is positive. And is it significant? And from up above, we know this is mildly significant. Should the linear regression line be used outside of the domain? And the answer is it could. But if you do, you want to use a little bit of grain of salt. Like, it's not actually ideal to use it outside of the domain. And you're like, what the hell is the domain? Well, the domain is the fact that I start here at the percent of 23.9 or 24% to basically 25%. So if I am trying to predict outside of a percent of Americans that are below 23.99 or 24%, or above the 24.99 or 25%. I could use it to predict it. It's not going to be the best choice to predict it because, first of all, my correlation coefficient is only mildly significant, and I wouldn't necessarily use it to predict outside of that. So what is my standard deviation? Well, I'm actually going to show you my spreadsheet that I'm going to use, and my standard deviation, I got to be 70.4348. And you're like, oh, great, another spreadsheet. I'm so excited. Of course you are. Are there any outliers? Well, when I graphed this, there was no outliers. There were no points that seemed to be outside of the cluster, and since there were no points outside the cluster, there clearly were not any that were influential. I'm going to find my test statistics, and again, I'm going to use my LinEst, and it's going to give me a whole bunch of information and my t-score. I get to be in the 2.4878. My p-value, I get my p-value to be 0.02322. So, based on a 5% significance, what is the decision? Well, I can do it either by the critical value, or I could do it by my p-value. Since my p-value is less than my alpha, because this is my alpha is 5%. So my p-value is less than my alpha, so I know that the decision is to reject the hoe. And so I would say something about there is significant evidence to conclude there is a significant linear relationship between the percent of Americans living at or below poverty line and cellular usage per capita, because a correlation coefficient is significantly different from 0. So I would build something that looks like this. I would have my x as my independent, y is my dependent, a is the y part of the y-intercept, b is the slope. Why are you doing that? Well, because in statistics, that's how we write our equation. Y hat is equal to a plus bx. Or you might see it as y hat is equal to bx plus a. So that's why a is the y part of the y-intercept, and we talked about that being an ordered pair. Y-intercepts should be ordered pairs. B is the slope of the line. Y hat is the predicted outcome. Y hat is equal to a plus bx is the line of best fit. R is my correlation coefficient. R squared is my coefficient of determination. I might see this as SSE or RSS, which is a sum of squares, errors, or the residual sum of squares. Depends on the book you use. S is my standard deviation or standard error of the estimate of the y estimate. T-score is my calculated t-score, which is my test statistic. My alpha is my significance level, and remember we are a two-tailed test, so I will find my t-alpha score, my t-score of alpha divided by 2. This is my critical value. It is not my test statistic, it is my critical value. Okay, so this is what I have, and I only need this, by the way, to check outliers. So here I have this where I'm going to put all of my independents, I'm going to put all of my dependents. I have y is equal to, y hat is equal to a plus bx. And you're like, where am I getting these numbers? Well, remember, I'm going to do my LinEst. And when I do my LinEst, here is my slope. So when I build my calculator, here, this one right here, I would do an equals, and I also have the y part of the y-intercept, so I'd grab that cell that has that. So when it's asking me to do y hat, these are my predicted y values. So I'm going to do my y hat, and I'm going to grab the cell that has this in it. So that is my y part of my y-intercept. That is my A cell, whatever cell that is for you. And then I'm going to do plus. I'm going to grab the cell that has my slope in it. So I'm going to grab that cell that is my B. And then I'm going to grab the cell that has my X in it. So then I'm going to multiply by the cell that has my X in it. And then that's going to give me my first value. Now, let's assume, for sake of argument, that these cells, because you're going to like, how am I going to do this? Well, let me show you how to do this so you can drag and drop. Let's assume that this is the column A, this is the column B. Let's assume this is row 3, and this is, say, row 27 and row 28. So what I would do to get this number is I would do an equal symbol in that cell. I would grab the cell that has my y part of my y-intercept, which is B27. Now remember, if I want to stabilize this, so then when I pull this thing down and go down like that, I am going to want to put dollar symbols before the B and after the B. So every time I pull that thing down, it's always going to grab this cell and it's not going to change. And then I'm going to do plus. I'm going to grab the cell that has my slope, which is this one. So let's assume this is A27. And once again, I'm going to make sure I put a dollar symbol before and the dollar symbol after. And what that does is to make sure when I pull this thing all the way down, it's going to stick with only these two cells. And then I'm going to make sure, because you're going to ask me, why isn't this working? I'm going to say, make sure you put a multiplication symbol there. And now you're going to go and grab the cell that has this, which is A and 3. I will not, by the way, put any dollar symbols around there, because when I pull this call all the way down, I want it to continue to pull all of these X values all the way down. What I don't want to happen is to pull these numbers other than what's here. That's where you put the dollar on either side of the B and the dollar on either side of the A. Okay, now that then gives me the ability, this is my predicted Y value, to figure out what my Y hat minus Y is. Well, this cell is easy. Okay, so this, if this is A, this is B, this is C, this is D. So in this cell, I'm going to do an equal symbol. I'm going to grab my cell, which is the one next to it, which is C3, and I'm going to subtract off what it was expected to be, which is in B3. Here is predicted, here is expected. Okay? All right. So then that gives me this, and once again, I'm going to highlight this, make sure I go down to the bottom corner and pull it all the way down as far as I need. Now what I need to do is do the absolute value of this, and I'm going to divide by 2 standard deviations. And you're like, why are you doing that? Because this is going to help me check for outliers. Now I said, hey, you can just do, like look at it, but this is truly going to check for outliers. So what we do is we take the absolute value of this number. So some of these numbers are negative, so I'm going to take the absolute value. So I'm going to do a call that is equals. I'm going to type in ABS, and I'm going to do a parentheses. I'm going to grab this cell, which is right here. This is the difference. This is A, this is B, this is C, this is D. So I'm going to take the absolute value of D3, that cell. Whatever your cell is, I'm just going to call my cell D3. So I'm going to grab D3, and then I'm going to divide by 2 times my standard deviation. And you're like, where is that coming from? Remember, I did the LinEst. I come down here. This is my standard deviation because that's where it is right here. So what I'm going to do is I'm going to do 2 times. I better make sure I have a parenthesis before that. And I'm going to grab that cell. For my cell, looks like it's just for sake of argument, we're going to call that 29. So I'm going to do, are you ready for this? A dollar symbol. And it is in B, and then a dollar symbol. And mine happened to be, for sake of argument, 29. And what'll happen then is when I pull this all the way down, it's going to always pull that cell, which is where my B29 is, which is where my standard deviation is. Now it says, hey, if this value is greater than 1, then that is considered an outlier. And I look through, yep, there's no number greater than 1. And so this actual spreadsheet of all the ones that we did isn't that bad. So that's pretty much it. Now, how do we get this? So that gives us all of that stuff, checking for outliers. My R, and it's going to be so easy, we're just going to put in equals. We're going to type in CORREL. We're going to grab the independent or the X values first, and I'm going to do the dependent, which is the Y values. Now this is kind of messed up, so if this doesn't mess you up, I don't know what is. I grab my X values here, but up here when I do my LinEst, right, I'm going to do my independence second. When I'm doing my correlation, I grab the column with my Y's, but when I'm doing my LinEst, I grab the column of Y's first. So be aware of that. Now here is my T alpha score divided by 2. This is my critical value. And so I do a T.invert.total. I grab my alpha. I divide by my degrees of freedom. And I don't have to worry about dividing by 2 because this two-tailed test does it for me. The degrees of freedom should be my n minus 1. So if I don't have n-1 somewhere, I got to make sure that I have it somewhere in my spreadsheet that I'm doing an n-1. And you're like, how am I supposed to do that? Well, you can always do, so degrees of freedom is going to be equal to, so what I'll do here is I'll do a count, and then I'm going to go grab either my X column or my Y column. I'm going to do that, and then I'm going to do -2. And that will give me my degrees of freedom. Now this should be all uppercase because it is an Excel call. So then I'll have my degrees of freedom, so I can grab my alpha, which is wherever I put that alpha. So I can put it, I probably should put my alpha here somewhere. Oh, here's my alpha. No, I need to put my alpha somewhere. Oh, I could probably put it there, and then I can grab the alpha here. And then of course my degrees of freedom is right there. My t-score, this is going to be r times the square root of the degrees of freedom. So I'm going to grab the cell that has my r, multiply it by the SQRT. This is r is the cell I'm grabbing. My degrees of freedom, which we know from up here is the count. And then I do divide by 1 minus. I'm going to grab the cell that has r in it. I'm going to square it. And then I'm going to do my p-value by doing the 2.dist, the absolute value of that t-score, so this cell right here, comma, the degrees of freedom, which is right here. And that's it for chapter 12.